Our invited speaker is Professor Dr. Truong from Birmingham University, and I am happy to see him here because it is really, I'm very lucky person because he was my supervisor during my PhD time. I've learned many things from him. Really, he's very gentle, respectful, and very helpful. Really, I've learned many things from him, and now I am conveying all those good things to my students and to my institutions as well. Thank you, Professor Pham. I would like to thank you once again. Really, I appreciate your support. Not only for PhD time, you are still supporting us. Thank you. And let me introduce to you first of all, and then I will give you this time, and you can continue. Is that okay?
Yes,
right.
Sure.
Okay. And Professor Dr. Pham is he has got many membership from different national and international institutions in the UK. And he's also in 2003, he's OB. OB means Officer of the Order of British Empire. And he is a distinguished person in the UK. And he's now the academic staff in Department of Mechanical Engineering in Birmingham University. He's a Chance Professor of Engineering, and also he's Director of Research at that university. And Professor Pham has made a wide-ranging contribution to the theory and practice of mechanical manufacturing and system engineering, and his academic output includes more than 500 technical papers and 15 books. And also, he has supervised more than 100 PhD students like me, and almost 200, as far as I remember, 20 Turkish PhD students he supervised. Thank you very much for your contribution to Turkish gentlemen. And also he has won in excess of 30 million pounds in external research grants and contracts. In addition to that, pursuing and leading research, he has also been very active with knowledge transfer to industry, applying the results of his work to help multinational companies, SMEs, to generate wealth and create and safeguard jobs. He has lectured extensively abroad on his research, and he acted as a consultant to several major companies. He was also invited professor to ECO Central to Paris, and consulting professor at Hughes, China, and also visiting fellow at University of Canterbury, New Zealand, and also visiting professor at University of Paul Verlaine, France, and also visiting professor at King's University, Saudi Arabia. And he's currently strategic scientist at Huan University of Technology. And he is recipient of several prizes as well. Sir Joseph Whiteworth Prize, awarded by the Institution of Mechanical Engineering in 1996 and 2000, and also the Institution of Thomas Stephen Group Prize in 2001 and 2003. And also Donald Julian's Grown Prize in 2004, and the 5th ICMR Best Prize, Paper Prize in 2007. He is also Fellow of Royal Academy of Engineering and Learned Society of Wales and Society of Manufacturing Engineering, Institution of Engineering and Technology, and Institution of Mechanical Engineers. And he was made on OB in 2003, New Year Honors List of his service to engineering. And he has many features, but because of the time limitation, dear Professor Pham, I know your contribution, not only this, and also artificial intelligence, we know that, how you contributed in the field. Please, now it's your turn. Thank you very much again for your contribution to this presentation and to this talk series. And on behalf of our Gazi University Rector, I would like to thank you once again. He asked me to convey his regards to you for your contribution. Thank you, Professor. Please, it's now your turn. Thanks a lot.
Thank you very much, Sharif, for the very kind introduction. Thank you. I hope that everybody can hear me well. Yes.
Yeah, we are hearing you very well. Thank you.
Very good. Very good. I'd like to start sharing now the screen.
Please.
Yeah. So please bear with me. So this is the one, and I need to be sure that I also share the. I need to be sure that I also share the sound. Yeah. Okay, that's good. Okay, so now share. Yes, can you see my screen yet?
Yep.
Okay.
Yep, this
I will make it large now.
Yes, please.
Takes a bit of time to. Yeah. Can you see it now?
Yeah, fantastic. Thank you.
Okay. Thank you very much. So, merhaba. I still remember some Turkish.
Yes, sure. Yeah, thank you. Merhaba, dear Professor.
Thank you very much for asking me to make this presentation, Sharif. It's my pleasure to speak to you and your faculty. The presentation is quite a simple one. Let me just tell you the structure. I don't know why it is not moving. Let me see. I don't know. It seems, yeah, there we are. So it has 4 parts. The introduction is very brief. The preamble is very brief. Then I start to explain to you what remanufacturing is, and very briefly what smart remanufacturing is. Then I talk about the project that we've been working on, which is to do with robotic disassembly. And I'll explain the relationship between that project and remanufacturing, and then finally conclude. I've given about 40 to 45 minutes for the presentation, as Sharif explained to me before. So if I exceed this time, please stop me. Yeah.
Thank you.
Very good. So let me see. I will also start the clock. I have a clock. Yeah, there we are. Right. So seems that my presentation seems to be stuck a bit. I don't know why. Yeah. Okay. So as Sharif said, my institution is in Birmingham, and Birmingham is at the heart of England. So I draw the heart here. It is very close to London. By train, it takes only 80 minutes. And when the fast train runs, it will be 40 minutes by train from London. So it's really very close. Birmingham is the second city in the UK. So the second largest city. The first one, obviously, is the capital, London. Our university was established more than 100 years ago. And it has now 30,000 students and 6,000 staff. The first international student was established, again, more than 100 years ago. So far, we've been associated with 11 Nobel Prize winners. The latest one was in, I think, 2017 or 16. So it was Nobel Prize winner in chemistry and Nobel Prize winner in physics at that time. Yeah. So that's our university. And now I will say a few words about remanufacturing. But let's start first with what we all know, which is manufacturing. And as we all know, manufacturing is the process of converting raw materials here, into products that we use and throw away. This is the normal life cycle of a product. Yeah, we make the product from raw materials, we use the product and we dispose of it. in the new circular economy, this disposal takes place rarely. So when the product is finished, when we're finished with the product, we either can reuse it or we repair it and reuse it. So for example, I have a table at home which we bought for our dining room. So after a few years, the table got a little bit old. I wanted to buy a new table for the dining room. So I bought a table for the dining room, and the table in the dining room, the old one, I take it to the kitchen and reuse it. So that's reuse. If there's something wrong with the table, I might put a bit of varnish on it and make it look good, and I can reuse it in the kitchen. Or if something is really desperately wrong, then I break down the table into wood, and I take the wood and make something else with it. It could be another table, it could be a chair or something. So that is recycling, converting the product into raw materials again that you use to make other products. Remanufacturing is a loop that is in between. So this is the middle loop. This middle loop here is remanufacturing. So you convert the product into components, and then with the components you make a new product. So it is in between reuse and recycle. Now, as you go from inside here to outside here, you spend more energy. So least energy is needed here, a little bit more energy is needed here, and quite a lot more energy is needed for this loop. Yeah. So the best loop is obviously to reuse, but it's not always possible. So in fact, rarely is it possible to reuse something. So remanufacture is very good alternative. And as I said, it is part of the circular economy, which is now a big area for the European Commission. And I will mention that again at the end of the talk. My presentation seems to be stuck. I keep pressing and nothing moves. Okay, so let's see if this one moves. Now it moves. So what is remanufacturing? This is the definition in the British Standard. So it is the process of returning a product to at least its original performance. So notice this, at least its original performance, with a warranty that is equivalent to or even better than that of the newly manufactured product. Yeah, so this is not what you probably are familiar with, which is reconditioning. You know, when you recondition a product, you bring it to a working condition, but it won't be as good necessarily as a new product. Here, you bring the product to at least as good as new. This is another definition of remanufacturing according to the American standard. Okay, so American standard says like new or better than new. So these are highlighted words, like new or better than new. So here are some examples of remanufactured products. We have a piece of pipe here, and after remanufacture, it becomes like this. It looks like new. Here, another piece of equipment as new, a pump as new, and so on. Piece of electronic equipment as new. Or maybe inside you have a new processor, a processor that is of a new standard. You know, instead of i5, now you have i7 chip. And therefore, this product is better than the original product that had the i5 chip in it. Okay, so some people might wonder why a remanufactured product can be better than the original. Well, it is better because some components in it are better than the original components. So why do we want to do remanufacturing? Well, we heard a little bit about it before, but here is some statistics for you. This is some data taken from a book by Steinhilper about 20 years ago. He wrote it, maybe longer than that. Yeah, just over 20 years ago. And he compared the energy required when remanufacturing alternators, yeah, and manufacturing alternators from new. So if you say manufacturing alternator from new requires 100% of energy, then remanufacturing only requires 14% or even 9% in some cases. Yeah. So alternators and starter motors are here. Alternators 14%, starter motors 9%. In terms of material consumption, if you use raw materials to produce new alternators or new starter motors, and you say that is 100% of the material, then in remanufacturing you only need 12% or 11% in the case of starters. Let's say around 10%. So a big reduction in energy and in raw material requirement. Here is a concrete example. Caterpillar is a partner in our project. They are a big American company making earth-moving equipment and building equipment and so on. And you can see the kinds of savings they can make. So in terms of water use, 93% less water. Energy, more than 80% less. And material, 96% or 90% less. And more savings. Landfill, normally when you dispose of product, you have to bury it in the land. You need the land to bury it in. And landfill space needed is now more than 90%, more than 99% less. So you only use 1% of the landfill that is needed. So a lot of savings. In terms of greenhouse gas emission, 61% less. So a lot of savings for the environment, for resources, and so forth. So that makes sense. That's why we need to do remanufacturing. My thing is stuck again. I don't know why, Sarah. Yeah. So a problem in remanufacturing is uncertainties. You can see here is the condition of products when they are brought back for remanufacture. This is good. This is quite good conditions. You see at least these motors or alternators or pumps, they look reasonable. Here is what you might find in the scrap heap. So there is a lot of uncertainties in the condition of these products, and that makes remanufacturing not easy at all. So I will look at some issues in remanufacturing. So the key issue, as I mentioned, is uncertainties. There's supply uncertainties. You don't know the quality of the product that you bring back. You don't know the quantity of the product. You don't know how many motors are coming back today. How many will come back tomorrow? You don't know. You don't know the timing, whether they come this month or next month. You don't know at all. So this is a problem for manufacturing or remanufacturing. Because you don't know the condition of these products, you don't know how much effort you need in order to repair or remanufacture the products. You don't know the time required to remanufacture the products. So you cannot estimate when the new remanufactured product is available. You don't know how much it will cost, because that will depend on the remanufacturing effort. If you need to put a lot of time in, if you need to replace a lot of components, then the remanufactured product will cost more. So you don't know that. So all that poses problems for remanufacturing. Now, smart remanufacturing is in order to overcome these uncertainties. You can overcome them by using sensors. You embed sensors in products to monitor the condition of the product continuously during the use of the product. And then because of that, you know when the product will come near the end of its life. So you can predict the life of the product. You can predict when it will become available for remanufacturing. And then you have also a complete record of the life cycle of the product. You know how it has been used. Therefore, you can know that, let's say, certain bearings will need to change, certain components will need to be repaired, and so on. You know, a shaft is nearly broken and you need to repair it or you need to replace it. So this makes uncertainties, this reduces uncertainties and makes life easier for remanufacturers. Now, let's look into the a typical remanufacturing process. So here is the end-of-life product, the product that has reached the end of its life. The first operation that happens is that the product is disassembled. You take it apart, you break it down, then you clean it thoroughly, then you inspect the different components. Then those components that are repairable, you repair them. Let's say if there is a bit of wear in the component, so you can build it up. You can use additive manufacturing to build it up. Or if you cannot repair it, then you can replace it with a new component. But hopefully the replacement is not too expensive. You don't have to replace too many components. The most expensive components you can reuse. So that makes life easier for you, makes costs less for you. Then after you have got all the components, either new or repaired or completely reused, then you can reassemble them. After you have reassembled the product, you test it thoroughly. So you put it through the test regime in the same way as a new product would go through. And after the test regime, then you can dispatch the product for reuse, for people to use. You can sell the product to customers again. Okay. So at this point, the product is like new and it has a warranty that is as a new product. Now, you may ask how many times the product can go through this. Is it once, twice? No. In some cases, this loop can happen many times. Now, at Caterpillar, they have some products that have been through this process 7 times. You know, 7 times this. And each time can be 5, 10 years. So the product can last a long time. I have this slide, and I would like to ask people in the audience to think about the slide and tell me, let's say if Sheriff, you can tell me what I'm trying to show here.
Okay, now I open the microphone. What you are doing, you are assembling new manufacturing. No, it's just repairing, maybe just replacing or something. Just I'm trying to understand the video.
Yeah, okay. So I'm showing the disassembly. You know, this person is disassembling a turbocharger. Right. These people, they are disassembling a big engine, a big engine. You can see the size of the people and the engine. And you can see that this requires a lot of effort, a lot of manual work, yeah, a lot of people, a lot of effort. This is very skilled. You know, the person does a very skilled job. So disassembly is a difficult operation that requires a lot of manual labor. So this is what makes remanufacturing currently not completely automatable. You know, you cannot automate disassembly. You cannot make remanufacturing autonomous. Our research program called Auto Reman, yeah, It stands for autonomous remanufacture. And we address the problem of disassembly. You know, problem that I showed on the previous slide, with a lot of people being used, a lot of skills being required. And our project addresses this problem. This is a 5-year project, and we adopt a fundamental approach to the project. We want to study the science. So this is why this this talk fits your series, which is engineering science talks. Yeah. So we are talking about developing the science of disassembly, to understand disassembly fully. We adopt a scientific approach to studying the problem of disassembly in remanufacturing. And our project is called Autonomous Remanufacturing, or Auto Reman. And you can see here robots being used and people being involved, and robots doing some work autonomously or collaboratively with people. In this case, again, autonomously, in this case, collaboratively with people. Yeah. So this is our project. So the first step of the project is to understand disassembly. So to look at disassembly science, we study the individual disassembly processes to understand the informatics, the information content, and the mechanics involved. So informatics is of interest to you, of course. We get this understanding in order to develop practical disassembly strategies. Yeah, we want to develop strategies that can enable robots to perform disassembly in a reliable manner. And because we want to have autonomous remanufacturing, we want robots to be able to plan their operations. So we study disassembly planning by robots. Now, in some cases, the plan doesn't work. The original plan doesn't work. So the plan has to be done online. Replanning has to happen. If the robot is working and it finds that it gets stuck, then it has to replan the operation. So we study planning and replanning as well. Then it's stuck again. Yeah. So collaborative disassembly. Now, we realize that with a lot of efforts, you can achieve totally autonomous disassembly, but it will cost a lot of money. So collaboration between humans and robots are necessary from an economic point of view, at least. And in some other cases, obviously, you can use robots to replace people in dangerous situations. I will return to this shortly. But these are the 4 main parts of our project. The final part is to construct demonstrations of the strategies and techniques and the tools that we developed in the previous 4 work packages. So here are the 5 work packages of our project. Our project is a 5-year project. It started almost 5 years ago, and it is in the final year. There are 6 more months to go, and I'm going to describe to you what we have achieved so far. So we have been studying disassembly science. We have been looking at individual disassembly processes to understand, as I said, the mechanics of the processes and also the information content of these processes. We have used our understanding to develop strategies to enable robots to perform those individual disassembly operations. And as I mentioned, we've also been studying disassembly planning. Collaborative disassembly is the next piece of work. So when people and robots work together, we look at that. And then we have constructed demonstrations of our work. So I'm going to say a few words about each of these work packages. Before we started the disassembly science work package, we need to identify the fundamental disassembly operations. So we studied many projects, many products. In total, more than 400 products. We looked at more than 400 products to see how they are disassembled, to see what operations are involved. So we found something like 12,000 operations. And then to classify those operations into categories. And unsurprisingly, we found that unscrewing is the largest category. About 40% of operations involve unscrewing of some sort. So unscrewing is a fundamental operation that we will study. We found that also separation. Now, separation is a big category. It involves all kinds of operations. But there is another class, 20% of the operations involve pulling. So imagine you have a bearing that is in the housing and you pull the bearing out. So you pull it in one direction, or you pull the shaft from a bearing. So these operations are known as the peg hole operation. So people in robotics have studied peg hole assembly of a cylindrical peg into a cylindrical hole. Now we look at the pulling of a peg from a hole, like the operation that I showed you earlier. Okay, so these are what we found initially before we studied the different disassembly operations. And there were two particular operations that we studied in detail. And they were the unscrewing operations and the pulling operations. We have yet to look at separation operations. So we benefit a lot from studies by people who look at screwing as assembly. And we are interested in disassembly. So when people look at screwing as assembly, they want to screw securely. And they are worried about vibrations. You know, when you drive your car, you don't want the vibrations to make your wheels loose. So people looked for a number of years at how to make screws that do not loosen when they are vibrated. In our case, we are interested in using vibrations to loosen the screws. So we have a project in this area, and there is a very, very capable researcher who is looking into self-loosening processes. And he's devising a tool to make the screws loosen by themselves. So this is a part of our work. Another project in the area of screws is to look at the efforts required to unscrew screws of different conditions. As you saw before, when the product is brought back for remanufacture, the parts are not clean, they are not new, they may be rusty. And we have created rusty parts, rusted components artificially in the lab. And we have looked at what efforts are required to unscrew such components. So here, by putting a bit of lubricant on, you can reduce the effort. But by heating the components, you reduce the effort even more. So this is what we have found. You know, the use of heat is very good in unscrewing. The use of lubricants is good, but not as good as heat. If you can apply heat, this is recommended. So this is one finding in our work. Now looking at the pulling operation. So here we are interested in pulling the cylindrical pin from the hole. I have exaggerated here, showing that there is a big clearance between the pin and the hole. But in practice, the clearance is very small in terms of microns. And if you are not careful, when you pull the pin out of the hole, the pin can get stuck and we studied the forces involved and developed strategies to enable the robot to pull the pin from the hole without the thing getting stuck. So you can find more information on this in a paper that was published a year ago by our team. Now, the previous slide showed the robot fitted with sensors, and it used 4 sensors in its hand to determine how to move in order to avoid jamming and wedging the pin in the hole. Here, instead of using force sensing, we enable passive compliance. So there's a spring, a well-designed spring that enables the pin to be pulled out of the hole with minimum stress. So when you use our device, then the stresses are low, as indicated by the blue color. When there is no device, and when you just try to pull the pin out without compliance, then you can see the stress build up as the red color shows. So the stresses are very high. So passive compliance can be used to help. Here we look at a pulling operation, but in a different way. So we are pulling this pin out of the slot. We pull it along the slot, and you see the robot here started before, but the robot here finished its operation before this one. The one on the left-hand side is still struggling. And the difference between the two is that on the left-hand side, we use vibration. So here again, we see the importance of vibration. Instead of teaching the robot how to perform the operation, we can let the robot learn by itself. So here we let the robot learn the pulling operation by reinforcement learning. So reinforcement learning of that particular operation. And I illustrate to you here. So at the beginning, the robot fails. Yeah, it gives up. It gives up. It gives up after a bit of pulling. But at the end, you can see it has learned how to move the pin along the hole without being taught, by maximizing the reward. So there is a reward function, and the robot learns by maximizing the reward. Yeah, now it can do the operation after something like 40 periods of learning. So finished. Let's pull it out. Yeah. So our project involves, as I said, multidisciplinary, mechanical engineering, manufacturing engineering, computer science. You can see machine learning there. So here is some more mechanical engineering for you, because I come from mechanical engineering, and you can see that vibration is also helpful. Here we are pushing the pin from the hole, not pulling it, but pushing it, and the pin is locked in the hole because it is press fit. So again, using vibration, you can reduce the effort. Using vibration, you reduce the effort greatly. Yeah. Here again, the pin is wedged in the hole, and using vibration, you can unwedge it. So you can see, you unwedge the hole after vibrating the pin. So vibration is very helpful in disassembly. It's not helpful for assembly, but very helpful for disassembly. Now talking about planning. So here is an example, very simple example of a planning problem. We want to disassemble this water pump. And the water pump is very simple, has only 6 components. Yeah, 1, 2, 3, 4, 5, 6. And the disassembly plan is quite simple. You can devise it by hand. So here is one plan. Yeah, one plan. The next plan is shown here. Yeah, and the third plan is shown here. And you can see that by planning properly, you can shorten the plan. You can reduce the number of steps. Now, this is a simple operation. When you have a complex operation, the plan cannot be designed by hand, and you need to use the computer. You need to use computer science to do it. And we have a technique known as the Bayes algorithm. And Sheriff might know the Bayes algorithm, which is designed by our team. And using the Bayes algorithm, we can optimize the plan. And this can have hundreds of components, and optimizing by hand would take hundreds of years. But we are able to do this online in real time. Collaboration is important to our project because, as I mentioned before, in some cases, although it is very possible to make the robots do the entire disassembly operation, it is not economic to do so because you need a lot of tools and fixtures, and it costs money. So it is good to have human-robot collaboration. And this shows here three methods of human-robot collaboration. In one case, people and robots work together, but their spaces are separated. So people and robots are in different spaces. They work together on the same task, but they are separated in space. Here, they have the same space, but when the person comes in, then the robot slows down or even stops. Here, this is true collaboration, where people and robots work together and there is nothing separating them. Now, this is possible because of the new generation of machines known as cobots. You can buy these cobots now, and they are quite inexpensive now compared to previously. They are, you can get cobots that are as cheap as normal robots, as industrial robots. So cobots are expected to be used more and more in the future. Oops. Now about our demonstration. We have constructed so far two demonstrations. One is the disassembly of a water pump. I showed you the water pump before, and in our cell, we have two robots and a person working, and there is a tool here that the person operates. We constructed this demonstration to show human-robot collaboration. In reality, you may not design a cell in this way. You may be able to construct a completely automated cell. For instance, by automating the press. Here we use only a manual press, and the person operates the press. So this is a press. And the press is used because in the part there are some press fit components. So this is a press fit component. This component needs to be pressed out of the holder. You need to use quite a bit of force, and the robot doesn't have that force. Even the human cannot apply this force. It is hundreds of kilograms. So the person has to use a tool, and the tool is a press machine. Yeah. So when the person uses a tool with one hand, the person catches the part out that comes out. So the shaft, when it comes out, is caught by hand. In our case, we use a robot to free the person so that the person doesn't catch the robot. The robot catches the component to help the person. Yeah. So just to illustrate, the robot helping the person. So you see, the person uses the press, and the robot waits here for the part to come out. Yeah, you see the person pressing, and the part comes out on top. Yeah, it comes out. It touches the hand of the robot. The robot comes up and picks up the part. Yeah, so you can see. Yeah, so the robot waits. The pressing is done. Yeah, the pressing is done. You see, and then the part comes out gradually. If you focus on here, you see it comes out gradually, and then the robot catches it. In that was the first case. The second case is when the robot holds the part. It is holding the part as the pressing is done, and the robot follows the part. It is compliant. It is able to follow the part as it is coming out, as the part comes out. Yeah, notice again. So the part is being pressed, the robot holds the part and it comes out. You can see the hand of the robot going down. The hand goes down. You can see, if you watch the bottom screen, you see, yeah, the hand goes down. So there's human robot collaboration there. Yeah. Now there is a video, a 3-minute video that I will not show, but you can find on YouTube. I show you the link later on. Here is another case of human robot collaboration. So you can see the person, the operator, and the two robots. And in this case, we are disassembling a turbocharger. And you can see that the human is involved in working with the robot. And the human works on tasks that are difficult for the robots to carry out. So these tasks are difficult because the robot has a big tool and it cannot reach into a small space. So the person uses his hands and can reach into the small space and can perform the operation, whereas the robot will find it difficult. And on the top diagram, then you see person and robot working together. Sorry, the two robots working together. So here you have robot collaboration. One robot holding the part while the other robot works on the part. So the robot here is unscrewing, is performing the unscrewing operation. And it searches for the screw. It does a searching operation. Yeah, it uses sensors and searches for the screw. Okay, so now we can see the video. Oops, I do beg your pardon. I go back to show you the video. Yeah. Okay. So the person starts the movement. So the robot picks up the turbocharger, puts it in a clamp, and the second robot comes and performs the unscrewing operation. Now you see the robot had to search for the head of the screw. It was not taught the exact position of the head because the exact position is not known. So it had to search for the head. You can see the searching operation here. Now you see the searching more. Searching, 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 searching. Found it. It performed a spiral search operation. It looked a bit random, but actually it was a spiral search. Now the person comes in and helps the robot because some operations are very difficult for the robot to perform. Now this operation is not easy for the robot either. So using a hammer to knock, because it involves knocking, it's a little bit difficult for the robot. So the person does it for the robot. And now he goes in and performs some very difficult operation here, because the robot cannot reach these areas. The person does it. So, in conclusion, the first step in remanufacturing is disassembly. And as I showed in one of the previous slides, it is a very intensive, labor-intensive operation, disassembly. And it's also very skilled. Our project, our auto reman project, focuses on developing a good understanding, a scientific understanding of disassembly to help robotize the process. So clearing the bottleneck that exists in remanufacturing and enabling us to develop smarter remanufacturing. Now, the EU Commissioner for the Environment wrote a few years ago that with the circular economy, we are looking at a triple win. Society wins because there are jobs for people to carry out. You know, disassembly may be something that we do for people, but people are involved in other parts of remanufacturing that robots cannot be involved in. So you create jobs in those areas. You save materials, you save energy, you save water. So that saves money for businesses. And of course, you save carbon emissions. So you save the environment. So there are three wins. And this is a major opportunity that people should really grasp. Now, we in Birmingham cannot do it alone. You know, we talk about human-robot collaboration. How about human-human collaboration? We want people to work with us in this area. And that's why we have set up a network known as the Auto Reman Network. And we invite people all over the world to join us. Our project currently has collaborators from Spain, from China, and we need more collaborators. Germany as well, we have some friends, but we need more people to work with us in this area. The Auto Reman project finishes this year, but the work on remanufacturing continues for a long time. I started my PhD in this area more than 40 years ago, and I'm still working in this area. Thank you very much, Sheriff. Thank you.
Okay, dear Professor, thank you very much indeed. Really, you provided us a good, different perspective, actually. We are looking at the industry from manufacturing side, but you gave us today different perspective. We have to look at also another perspective from disassembling side, how it is really difficult part of the industrial process, actually. Thanks again, and we have some questions. Let me reread from some people. Thanks to Professor PHAM for the presentation and sharing invaluable knowledge. I would like to ask the professor how many projects did he and his team accomplish by making remanufacturing? How much financial return on investment for the partners? These partners might be city, governor, or company. Could you give us some examples for emphasizing the importance of remanufacturing? One of the colleagues asked you, Professor. Actually, you have already mentioned some of them and how, what sort of examples you've done with the industry, but you know, that was the one of the questions I directed to you.
Thank you very much, Sheriff. So our project is a fundamental research project. This particular Auto Reman project is fundamental. So we are not looking at implementing this in industry right now. We had two other projects. Both of them have finished, which were related. One was also to do with disassembly. The other one was more to do with the circular economy. We are looking at developing more projects. The next project we are working on is disassembly of batteries for electric vehicles. So, you know, in a few months' time, we will have a demonstration of the use of robots for disassembling of car batteries, of the electric vehicle batteries. So to answer your question, we have 2 demonstration projects so far, and then the third one is going to be completed in a few months' time. We have not implemented these projects in industry because our project, our research project, is fundamental research.
Yeah, thank you, Professor. You know, it's, you know the problem, but you know, in order to solve the problem, you need really solve complex or the different problems in that, because it consists of many uncertainties inside as you initiated that, and also it combines collaboration, cooperation, and coexistence in the progress. Really is hard task in theory and practical side. You emphasize those very well. Thanks a lot. You know, it's personally, actually, you know, it's I focused on manufacturing side, but you know, its assembling side is really harder than manufacturing part. This sort of, I think, studies will help manufacturing side as well for the future development, I think. You know, how, while we are manufacturing any products, we also think of how disassembling those products in easier way. We'll think of those ideas in the future. Really, it is fantastic ideas as you promoted in our initial works as well. Really, thanks a lot. It's different perspective you are inserting in the science domain. Thanks a lot again. Okay, if we have any other questions, I am checking. Is there any raise up? Can ask Professor Pham. Any questions? Okay, dear Professor, you know, some students are also at the meeting. You can you suggest them some experience how this sort of achievement can be done? What is your suggestion for the future of the science? And you can maybe share one of your ideas or some of them you found it important.
So, Sheriff, at the moment we are very keen on studying the science of some more disassembly processes. You know, so far we have been looking at unscrewing and also pulling the pin from the hole. Now, there is a lot more work to be done in this area. You know, more than 50 years ago, people started looking at the insertion of a pin into a hole. And now, if you look around the world, there are still people doing PhDs on how to assemble a pin into a hole. So, you know, we only just started the looking at pulling the pin from a hole. I'm sure that in 10, 20 years' time, people will still be studying that process. So yes, if you have researchers at your university interested in going into this area, it's a very rich area. And I believe that they can make a career, start working in this area.
Yeah, I am sure some of our colleagues are listening, attending this talk, and I am sure in the near future they will contact you. And also, I am here. We can collaborate for future project, future development, and maybe for different practices in the industry. I'm sure it will help us to develop better science and better development, as you suggested, as you contributed in the field of science, actually. Thanks very much. Is there any other let me ask you a few questions, dear Professor. if I miss some of the. Oh, okay, Professor. Maybe I shared something on the screen. This time I shared. While we are asking questions to you, we have to share some appreciation certificate. Okay, there are some people are asking questions, but you know it's I couldn't grab actually the questions here. Anyway, for the future development, we can certainly collaborate in a different perspective. You are a very open person, I know, and you are also supporting this sort of activities. Thanks very much again. And our rector is also okay. Our rector is also is sending special thanks to you for your contribution, especially for our 95th year of anniversary of Gazi University establishment. So this will really help us to improve industrial perspective, how we can not only focus on manufacturing and also in disassembling those things will help really a lot. Thank you very much. And
thank you very much. You are very, very thoughtful, Sheriff.
Okay, there is professor said that there is a question. We need 15 engineers for disassembly operation if we use robots. Is this useful? I might have misunderstood. Sorry. Okay.
Please repeat the question for me because I did not hear it.
Yeah, actually, he says that he misunderstood. Actually, okay. Let me read the questions. Thank you, Professor PHAM, inspiring presentation. I want to ask if remanufacturing will create new jobs for young generation, and what is the UK's employment and education policy about new remanufacturing? Is there any? Sorry, let me read. Is there any program about remanufacturing in your university? Thank you.
Thank you very much for the very nice question. Yes, remanufacturing creates jobs. We are talking about some jobs that we want to automate, but in other areas, remanufacturing definitely creates jobs. In the UK, it employs something like 55,000 people. So it's quite a reasonable number of people employed in industry. In other countries, in the United States, even more people, a lot more people. I think 160,000 people are employed in the United States in remanufacturing. So there is a lot of new employment. In terms of the teaching at our university, we don't teach remanufacturing. We teach manufacturing. There is a lot of common material between manufacturing and remanufacturing. The key difference is really in the disassembly rather than assembly. So that's one key difference. And supply chains are also different. We talk about the reverse supply chain rather than the forward supply chain. So there is reverse supply chain to consider. So those are two main differences between remanufacturing and manufacturing. Because in remanufacturing, you also do assembly, you also do inspection, you also do additive manufacturing. So all those elements are common.
Yeah, and also about the opportunities, especially in your university, if a person would like to apply for this robotic disassembly for remanufacturing, one of the questions was that,
yes,
is it possible?
Of course it is. We are always welcoming excellent Turkish students to do PhDs with us. I forgot to mention that in our team currently, under my supervision, there are 10 PhD students working on this project. And there were 4 postdoctoral researchers working on the project until recently. One of them now has become a faculty member, and the other one has returned to China. So we currently have 2 postdoctoral researchers, but we are building the team so we can have more. And we are always welcoming PhD students from Turkey. Sheriff, you might remember our lab, our intelligent systems lab.
Yes, certainly.
At least 10 Turkish students in at that time, and many other nationalities as well. Yeah.
Yeah, sure. Really, you know, it's, while I was doing my PhD, I have learned many things from you, and also I have learned many things from our lab. It was international lab, actually. People from all over the world, really, it was a good harmony, a good environment, good place to learn many things, not only for PhD perspective and also cultural perspective and other things. Really, I appreciate a lot. I've learned many things. And thanks to you once more. And one of our colleagues is raising his hand. I'm not sure. Can you help us, Murat, to open the microphone for Attila? Professor Bıyıkoğlu, please. I am checking how I can open his microphone, but
I think he can open himself.
Yeah, he's dear Professor Bıyıkoğlu, you can open your microphone, but we can't hear you.
Okay, thank you very much. I want to thank Mr. Dr. Truong PHAM. It is a very helpful, interesting presentation. I just want to ask if there is an available a book for teaching students in the university. Is there an available book? Remanufacturing?
Yes, there are some books in this area. I will assemble a list, and I will send it to Professor Sagiolu, and he will pass to you. Is that okay?
Okay, thank you. Thank you very much.
We, in our team, we are producing a new book as well. And the book is more research orientated, and it focuses on disassembly planning. So our book is to do with disassembly planning. But I will give you a list of other very interesting, very good books in this area. They are not very new, but I will assemble a list for you. And if you are interested also, I can also send you some papers. I will send to Sheriff. Yeah.
Thank you. Thank you very much.
Yeah.
Goodbye.
Dear Professor, thank you very much indeed. And also, you know, I asked you a question about, you know, you are a very collaborative person. We know that you are open for collaboration. In this project, are you collaborating with universities? Certainly you are, I know. But what is the things that we can also enter your network for those?
Yeah. So Sheriff, just email us on that address, and we put you onto our network. Currently, the main activity of the network is an annual workshop. We held the first workshop in Birmingham, a physical workshop. The second workshop was in China. The third workshop was in Spain. And last year, the workshop was supposed to be in China, but because of the pandemic, we held it virtually. And this year, there is another workshop, but also held virtually. And this time, it's organized by our colleagues in China. And so that's one way of collaborating, you know, participating in workshops, networking. But also, you can do, you can send people to come and work with us.
Yeah, sure.
Send people to come and work for a couple of years with us, you know, PhD students can come for a couple of years, or preferably they can come and start their PhD with us and do their PhD with us. That's the
Yeah.
best way to collaborate.
Yeah.
And then
Okay.
the final way, Sharif, is to apply for European funding.
As well. Yeah, sure.
Yeah.
Sure. Actually, recently we got a European project. We got some support from them. Maybe we, Professor Buygoğlu can organize that. Maybe we can use those grants. We can talk about it later on.
Sure. Sure.
Some PhD students we can support from that project. Okay, dear professor, it is really very nice to see you here. Very nice to talk to you, and also it is wonderful for delivering a speech. Is a wonderful presentation. Really, we are appreciating a lot for your support and for your kindness. On behalf of Gazi University and Engineering Faculty, I would like to once more thank to you for your really presentation, and hope to see you soon in Birmingham or in Turkey, in Gazi University. Really, we miss you a lot, actually. There are some of your students attending this meeting. Maybe they might say hello to you. Let me check. Shahin is here, by the way.
Oh, Shahin is with you.
Yes. Dear Shahin, you might say hello to dear our supervisor, by the way.
Oh, I did not know Shahin was in the audience. Oh, I did not know.
Shahin is there, and let me check.
Sir, nice to see you again.
Oh, hello, Shahin.
Is your
Hello.
lighting okay?
Yeah. What about your video? We can't see you.
Everything is good. I want to give you regards from Kayseri. I would like to see you in Kayseri also, maybe in Gazi University, Erciyes University. Nice.
Thank you very much. Thank you very much. We can't see you though. We can only see your name.
Only name is there, but no. Can you open your video, please?
It's open.
It is, but we can't see you, Shahin, dear Shahin. Sorry about that. Dear professor, all your students are professors at universities now in Turkey.
Yes.
Really, we appreciate you a lot. Thank you very much indeed. Yeah, I don't know what I can say more, but
Oh, you're very kind.
Except our appreciation. We learned many things, and we are now delivering those what we've learned from you. Thanks very much indeed.
And I learned from you another thing. Teşekkür ederim.
No, we say teşekkür ederiz, dear professor. Thanks a lot, really. And hope to see you soon. And
yes.
Also we wish you a very healthy life and long life. And
thank you so much.
Thanks a lot.
Yes. Thank you very much. We hope to see you soon and wish you all the best. Long life, happy life.
Yeah, happy life. Thank you. Bye-bye, professor.
Bye-bye now.
See you.
Bye.
See you.
Bye. Bye, Shahin. Bye.
Hi, Professor.